Okay, chemistry, we are going to work on your chemistry number 3 worksheet. If we started it in class, we can continue on. But for the year that I am recording this for, we have not even started the worksheet. So we're going to go through the entire thing, hopefully slow enough that you can follow, but fast enough that this video isn't forever long. So have your worksheet, have a pencil because you're going to take notes as I go. So this is what the worksheet looks like, and it starts with the law of definite proportions. So what you're going to turn into me on Thursday is this completed worksheet. Some of it I'm going to give you the answers to, and others leave blank so that you work it out. But the law of definite proportions, let's start here. The proportion of elements in any compound is always the same. That is the word for that section right there. It should be the word same. You're going to enter that in. Okay. Next one. A chemist wants to find the proportion for potassium chloride and adds 15 grams of potassium, which is the letter K, and with 15 grams of chloride, which is capital C, lowercase l. That's not an I. A lot of people get confused. After the reaction, she has 27.5 grams of potassium chloride and 10.5 grams of potassium left over. The chemist wants 50 grams of potassium chloride, no leftovers. How much should each element should she use? All right, so we're going to just pull out our information. I'm going to turn this in red so you know what's been new. We've got 15 grams of potassium, and we're going to add it. Oops, not F's. It's supposed to be a G. Sorry, easy to typo here. And we've got 15 grams of chloride, and that yields 27.5 grams of potassium chloride and probably with a plus sign, 2.5 grams of regular potassium. That's what they told us so far. So what we're going to do is we're going to put that into a ratio. So for every grams of potassium, we're going to create a gram over here. So we're going to put potassium over potassium chloride because we know how much of them we used. We used all the chloride, so we can start there. It doesn't really matter which one you use. So 15.0 grams of chloride divided by the end result of 27.5 potassium chloride is going to be equal to X number of grams of chloride over 50 grams of potassium chloride. Okay, so I took how many we used and how much we got, and I want to say, how much do I need if I need 50? So then you're going to do that math. So 15 divided by 27.5 times 50, and that's, where you're going to get the number. For potassium, you're going to end up with 22.7 grams. And then you could do the same ratio for chloride. You could say, because we started with 15 and 2.5 were left, you could subtract them, which would give you 12.5 and create your ratio. Or if you know you need 50, you just subtract, you say 50, subtract 22.7, and that would give you 27.3 grams of chloride. That's what's left, because you cannot create or destroy matter. It just changes forms. And we're going to have it change from a potassium and a chloride separate to a potassium chloride together. And this gives us 50 grams KCl. All right, so the next one. A chemist decomposes 40 grams of yellow powder into 24 grams of calcium and an unknown amount of helium gas. The chemist uses the proportion to make a kilogram of the yellow powder. How much calcium and helium is needed without any excess? Okay, so decomposes means you're going to take a big thing and break it down. So we have our 40 on one side. Let's make this red again so you know where I'm working. Sorry, I don't normally do it this way. I do it on a whiteboard, but I'm just trying it out. So your feedback is welcome. We have 50 grams. We're going to break it into, oh guys, seriously. We're going to break it into 24 grams of calcium and some amount of gram of helium. How could we find that? We just subtract. We have 40 and we give away 24. So we are left with 16. Okay, so that number, they didn't give it to me. I had to go find it. I had to do a little bit of math of subtracting, and this is how I got my helium, capital H, okay? We're gonna use our same proportions that we started with because now we want 1 kilogram. Now, in my last proportion, we did not use kilograms, so I can't use them here. So I need to change my 1 kilogram into grams. So I hope you remember, and I could do this down here for you if that helps you to move. But kilo is usually a pretty easy one. It means 1,000. So we want 1,000 grams of something. And this time we're going to make it. And so we're going to say, hey, what was needed to make that thing? So we use our ratios. We have, I'm going to come over here, for every 24.0 grams of calcium, we made 40 grams of yellow powder. Okay, and that's going to be equal to some amount of calcium, we don't know, divided by 1,000 grams of yellow powder. Those proportions do not change. That's like the number one thing. The law of proportion is they stay the same. So we do this 24 divided by 40 times 1,000. We end up with 600 grams of calcium. We do the math. I'd like you to figure out that number on your own, please, because this is grams of helium. I'm pretty sure you can figure it out, okay? And come with that number, and that will give us the beginnings. All right, let's move on to Dalton's atomic theory. You might have to pause, do some adding, subtracting, what you got to do. Dalton's atomic theory. All right. All elements are composed of small, indivisible particles, which means they can't break down any smaller particles called atoms. Yeah, I'm not going to make it look nice. You guys can do that. Okay. All atoms of the same element have exactly the same properties. They're all going to do the same thing. They're going to boil at the same rate and melt at the same rate and bond in the same way, same properties. Okay. Atoms of different elements, this might be a surprise for you, team. Atoms of different elements would then have different properties. Okay. Hopefully that one, you're just tracking with me. Number 4. So the reason I'm highlighting this is because your test asks you these questions. Number 4, blank are formed when atoms are joined together in simple whole number ratios. Well, what is formed? Compounds are formed. Okay. So you're going to write those numbers and words down. Okay, here we go. Next one. Chemical symbol to a chemical formula. This says 2 hydrogens, 1 atom of sulfur, and 4 oxygens. So it says 1 atom of sulfur. We're assuming it's also 2 atoms of hydrogen and 4 atoms of oxygen. The first thing you might have to do is use your periodic table. I actually don't have one here. I'm going to pause. I'll get one for us. Okay, got my periodic table. That actually took so long, so I'm glad I paused it. The first thing we need to do, the name is given, but the symbol is not. And so the name was hydrogen, which most likely you are familiar with. Hydrogen is right here. I think you can see my cursor. You probably cannot see my finger. Hydrogen is an H. So if we go back to our worksheet here, 2 hydrogens, we're going to write an H2. We're going to make this a little h. That's how we write it, okay? Next, it says sulfur. So we got to go find sulfur. Oh, where'd I? Where'd it go? Ah, here we go. Here's sulfur. So if you need to read, most of them make sense, but not all of them. So sulfur starting with an S, it actually stays with an S. It's right here. Sulfur is just the periodic symbol of an S. So then we'd write S, and there's one of those. So if it's a 1, we leave it blank. We don't put a little 1 down there. Oxygen, let's go over here. Oxygen, there it is. Oxygen is an O, just one big O. So for our next one, we are going to write our big O, and then how many? There are 4. So then I'm going to write right here a little 4. Okay. I'm going to leave you to figure out sodium, nitrogen, and oxygen on your own. Sodium is a tricky one. Do not look for an SO. Sodium is actually Na. I'll give that one to you. I'll give that one because that one's tricky. It's an Na for sodium. I'll show it to you actually too. It's over here. And you guys, you don't have to memorize this yet, but it's coming. You will be required to know the first 20, just as a heads up. Here is sodium. It's Na. So that's what I wrote down for you. I'd like you to add numbers and do the nitrogen and the oxygen yourself. Okay, let's move on. Maybe I should make this bigger. Maybe that would be helpful. Who knows? I don't know what you're seeing. Next one, how many atoms are in the following molecules? So here we have KOH, and they are each their own element when they're all a capital letter. So we've got potassium, oxygen, and hydrogen. And if you look at their subtext there, nothing, nothing, nothing. So that's 1 each. So this one would have a total of 3. That's how many are there. Now, this next one has a big S and a little I. That little I is attached to the big S. That's silicone. So that's one thing. You don't count the S as 1 and the I as 1. The SI is together 1, and I can show you that here. Let's go find silicone. There it is. Number 14. That's an element. So some elements have 1 letter, like a carbon, nitrogen, oxygen. Some have 2 letters, like silicone, aluminum, chlorine, argon, but they don't ever have 3, okay? And the second letter is always a lowercase small letter. So that would be a 1. Here's our hydrogen again. It has a little 3, so that's 3 hydrogens. So we have 1 silicone and 3 hydrogens. We're looking at 4 right now. And then we get to F for fluorine. That's also a 1. So this would be a total of 5. Okay, I'm going to leave this last one to you. That's actually like a sugar molecule, like a glucose. So I'm going to let you add that one up and figure out what those ones are. Okay, now we're getting into bonding, and we're going to hit this so many times. So if you kind of miss it round 1, it's okay. It's coming back. But the more you can jump on this, the better you will be in the long term. Okay, ionic versus covalent. At least 1 metal atom. So the metal atoms are left the jagged line, and I'm going to show you what this jagged line is. And at least 1 non-metal atom. So it's a metal atom and a non-metal atom together, and that's what makes them ionic. So let me see if this periodic table has the jagged line for us. Let's see. Let's make it a little smaller. Okay. So the jagged line is usually right in here, but aluminum is a metal. These are metals. Okay, let me find your textbook because that has the jagged line that you're going to use. Okay. So usually, oh yeah, I gotta stop screen sharing. My bad. Here we go. I'm back. So here is the chart in your textbook. And they make it very, very clear, this jagged line here. That's aluminum, gallium. I don't even know how to say those ones, guys, for real. But you see the clear delineation between the green and this pink, this jagged line. And then we have one standalone. See him way over here? Oops, reflected. Hydrogen. Okay. Hydrogen goes with the pinks, with the pink side. So the ones that are obvious metals, like we know aluminum is a metal. We know tin is a metal. So even if you just know those two, because they're metals you're familiar with, you know that the green is the metal side. These are your metals, the green, because there's aluminum and there's tin. This is the metal side. So it's one atom from the metal side and one atom from the non-metal side, or one of each of those together makes it ionic. And we're going to get into more specifics of what makes it ionic chemically, but right now it is one from the metal side and one from the non-metal side. That's it. Okay. So on this image, let me screen share it again. Share. Okay. One here. So that's all the greens, all the way over here. Lithium, sodium, these are also considered metals. Okay. And then shared with one, and hydrogen would be over on the other side, one. So if you had a carbon as the non-metal and it bonded with a sodium on the metal side, that would make it ionic. Now, covalent, which is our other option, means they stay on their own side. So, oh shoot, you can't see this when I move it now. I gotta, stop sharing. I gotta get you to the other screen. There we go. Okay, we're back to the worksheet here. Hoping you're seeing the worksheet. I have to preview this message. Okay. So one metal, which is one from the left side of the jagged line, and one non-metal is an ionic. If a compound is made up of only non-metals, which is to the right of the jagged line, and includes that one special element called hydrogen, it is covalent. Okay. Covalent is synonymous with sharing, and ionic is synonymous with taking and giving. A little more of a selfish bit there. Okay. Okay. How to name something that is ionic. We're going to write this in. Now, this is also in your text. I make these worksheets to synthesize the information. Okay. How you name an ionic compound is you take the first atom and the first atom's name, and then you add it to like the second atom's name with an ending of "ide." That's it. So let's do an example. We're going to go back to our sheet here. Oop. Can you see this? This is hard. I'm not sure if you can see it. If you take a non-metal like chlorine and you're going to add it to a metal, which is sodium on the left-hand side here, it would be a sodium and a chlorine. So you take the ene off and you add an ide, you'd have a sodium chloride with the ionic rules. All right. Covalent naming is very similar, but it's enough different that you can tell the difference. Okay, covalent loves prefixes. It is a prefix based on the number of atoms. And so if you start, let's pick a covalent name. We can actually use this one up here because this guy's covalent. Let's put him down here as an example. Okay, this is a carbon and a hydrogen and an oxygen. And the numbers down below tell you how many. So here's our prefixes. So the prefix of a 1 is a mono. And it doesn't start with mono, so we don't need that. And then we need to get it all the way to 6. So the prefix of 6 is hexa. So this would be a hexacarbon, hexahydrogen, hexaoxygen, and then we change it and we end it with, oops, I don't want to make it little. We end with an ide. Very similar as the ionic, how you end it. Some of them also end with 8s and ites, but we're just going to keep it simple right now. So we're going to name it hexacarbon, hexahydrogen, hexaoxide. That would be how you would name this compound because it is covalent, because none of them are in the metal category left of the jagged line. Okay, I think you can take it from here. Oh, that's right. There's one other rule with the covalent naming. You don't use mono if it's the very first element. So I'm trying to think of one. Let's say it was CHO. call it CHO. You wouldn't say monocarbon, monohydrogen, monooxide. You just say carbon, because we don't say the monohydrogen, monooxide. That's how you would say this one. CHOs exist, but it's not a normally occurring molecule, so we don't need it. Okay, you're going to fill in the rest of these prefixes. That's on you. They're in the book. Don't just assume you know. Like number 2, we often think of bi, like a bicycle, but this actually uses di, as in dissect, cut into 2 pieces. Some pull from Latin and some pull from Greek. So don't get too caught up on those. So what I need to see on Thursday, I guess I can stop screen sharing, is you finishing this worksheet, filling in all the blanks that I didn't finish, as well as all the blanks I did, because that tells me you were listening. Okay. Have any questions? Please reach out.